Welcome everyone. In this video I'm going to do one of our tree diagram problems that we've been using to calculate out the positive predictive value and negative predictive value for some test. And so, okay, why don't we just go ahead and get right into it here. We have a disease that supposedly affects about 0.5% of the overall population. We have some tests, and we have a given sensitivity of 98% and a given specificity of 93%. We want to draw a tree diagram that models this situation here. And then after that, I have a few questions that we'll use this tree diagram for. So, okay. This specifies, right, we want to go ahead and start with 1 million people getting tested. And so I'm going to go ahead and draw out maybe at the very top. So we're starting off with 1 million people. Oops, already an extra comma, way too early. So, okay, 1 million people who are getting tested. This is what we're starting off with. And then we need to break this down into folks who actually have the condition and folks that do not. So we're going to go ahead here, say have condition, or in this case I guess we know that very specifically it's some rare disease. So have disease and do not have disease. Okay, and the way we do this is that we use this 0.5%. And so we have 1 million tested, and 0.5% of them are suspected to have this disease. And so, okay, I have a calculator. I'll go ahead and pull up. And the first thing is like 0.5 is already a decimal, but notice that this is also a percentage, right? If I had just done, regular old 0.5, this would be actually 50%. So 0.5 is equivalent to 50%. So the first thing that I need to do, I need to take our 0.5% and I need to divide that by 100 to get kind of the equivalent decimal form for 0.5%. And so you can see that it's actually 0.005 is the decimal form. Again, 0.5 would be the same as 50%. So, okay, a little bit confusing, right, with this already, it already looks like it's in decimal format, but that percentage sign is the key here. All right, and then we have to say, okay, 0.5% of 1 million people tested. So I'm going to go ahead and multiply by 1 million people. So 1, 2, 3, 4, 5, 6 zeros. Always paranoid that I'll get one of these wrong and have too many zeros. And so this comes down to 5,000 people are suspected to have the disease. Oops. All right, so therefore the people who do not have the disease, well, that should be everyone else. So this should be 995,000. I guess people would not have the disease. But let's go ahead and double check this really quick. Because again, so the way that I got this was that I knew that it needed to add up to 1 million people, right? They either have the disease or they don't have the disease. But the other way that you could do this, well, if 0.5% do have the disease, then that means that 99.5% of people do not have the disease. And again, we have to turn this into a decimal format. So we're going to go ahead and divide by 100. This is the percentage of people who should not have the disease in the decimal format. And then we would need to go ahead and multiply this by 1 million. So again, kind of 1 with 6 zeros after it. That looks good. And we should get this 995,000. So there's a couple different ways that you can go about calculating this out. And now we need to go ahead and break it down one more time. For the people who have the disease, this is where we're going to be using our sensitivity. So sensitivity. And we can break this down into our true positives and our false negatives. So true, in fact, I'm just going to go ahead and denote this. So for true positive, I'm going to use TP. And then for false negatives, I'm going to use FN for false negatives. So again, we've given up here that our sensitivity is 98%. So 98% of the time, this test gets it right for those who have the disease. And likewise, over here, we need to break this one down. And these are going to be with our specificity. And we have a specificity of 93%. Okay, and so that's, again, specificity for those who do not have the disease. 93% of the time, it gets it correct. So we have here the true negatives, and then we have some false positives. Because, again, these are people who do not have the disease, and so if it comes back positive, right, that's false. They don't have it. And likewise, if it comes back negative, that's true. They don't have the disease. So this is, again, where we need to use our calculator. Pull this up, and I'm going to start off for the folks who have the disease. So for the 5,000 people who actually have the disease, and I'm going to multiply this by 0.98. So again, that's the 98%, and we divided that by 100 to get it into the decimal format. And so, okay, it comes back with 4,900 are true positives. So it gets it correct, 4,900 times. So that means that there's 100 people out there, right, who got a false negative, who actually have the disease, and yet it's coming back and it's saying, oh, you don't have it, right? So you notice, again, I just made these add up to 5,000. Alternatively, right, if 98% of the time it gets it right, then we could say 2% of the time it gets it wrong. So I could do the 5,000 times 2%, which again in decimal format is going to be 0.02. And this would be another way to get that number of 100. All right, now for people who do not have the disease, again, let me pull up my calculator one more time. Looks like my computer's going a little bit slow. So for those who do not have the disease, the 995,000 people there, so 995,000 people, it gets it right 93% of the time, so 0.93 in decimal format. So, okay, getting it right in this case means that it comes out with a negative result, right? Because they don't have the disease, and it should tell them that they don't have the disease. So it should come up with a negative result here. So that's going to be 925,350. 925,350. 925,350. 925,350. And that means that 7% of the time it gets it wrong. So same thing, I'm going to go ahead and do second entry here to get the previous thing, and then I'm just going to change this to 7% or 0.07. And so 69,650. 69,650. All right, so now we have our tree diagram showing, okay, what are the true positives, what are the false negatives, what are the false positives, and what are the true negatives. And we go ahead and we have this all labeled out. And now we want to ask a question regarding this. So suppose Todd tested positive. So tested positive, notice that there's nothing in here if we're talking about the PPV or the NPV. So in this case, the tested positive, this is talking about the positive predictive value. We want the positive predictive value. What is the probability that Todd actually has the disease? So for the positive predictive value, right, you're interested in all the things that you have, are positive. So for instance, we have the true positives. So the true positives, and then we're going to go ahead and divide that by all of the positives. So that's going to include the true positives, but then also the false positives. And this right here is the formula for the PPV, the positive predictive value. So in our case, our true positives are the 4,900, and then we have divided by the 4,900, plus we have another 69,650 people who came back positive. And again, that's only 7%, but it's actually still a very large number. And so let's go ahead and calculate this out and see what this positive predictive value is. So again, 4,900, we're going to go ahead and divide that by, and I'm going to use parentheses here because we have to divide it by, a couple things. We have to divide it by the 4,900, but then we also add on the 69,650. So these parentheses are very important to divide by all of this. All right, so I get 0.06, we'll say 6 after rounding. So 0.066, or that's the same thing as 6.6%. So the probability that Todd actually has the disease, even though he tested positive, right, is only 6.6%. And that's because, again, there are so many false positives in this. All right, on the other hand, we have Joe. Joe tested negative using this test. What is the probability that Joe does not have the disease? Well, again, nowhere in here does it say PPV or NPV, right? So we have to realize that when you say tested negative, we're interested in the negative predictive value. And very similar to the positive predictive value, right, there's a nice formula for this. You want to know the times that it got it right, being negative. So we have the true negatives here. But then we're going to divide by our true negatives, but then there are some other negatives out there. We have false negatives. So we basically have the true negatives divided by all of the negatives. So in this case, our true negatives are 925,350. And then, again, our true negatives, 925,350. But then we also have some false negatives. We have an extra 100 or so. So, okay, again, I'm going to get out my calculator here. And let's see, 925,350 divided by, and this is where we need to use our parentheses here. And again, 925,350, but then we have adding on an extra 100 people who have some false negatives. And all right, so this comes back 99.9% of the time. So this would be 0.999, or that's the same thing as 99.9% of the time. If you receive the test as negative, right, that is a true negative. So there's only, a very small fraction, these extra 100 people or so right here, compared to this 925,350, right? Almost all of those are true negatives. And so that's why this is such a high percentage here. All right, so with that, I hope that you've found this video useful, and if this is well modeled, kind of this tree diagram method that we have here for calculating out the positive predictive value and the negative predictive value. All right, good luck studying for the final exams, everyone, and have a great summer.